Hi everyone, and welcome back to our next video in the VHDL design series. The last video we talked about CPLDs and how CPLDs are used in the industry, and more specifically the hardware, how the hardware is configured internally and what they're best used for. So in this video we're going to be exploring the use of FPGAs, which is tends to be quite a bit of the industry as far as the application of programmable logic. There's a wide diversity of components that are FPGAs with multiple pinout options and cell density options and just a whole slew of things. That seems to be where the greatest growth is happening in programmable logic, is in the FPGA arena. And we're seeing lots of different devices that are coming out with new features. So we're going to talk about how a basic FPGA works internally, what the structure looks like, how they handle combinational logic, and basically how they function inside. And we're going to go do some examples of implementing some designs using VHDL hardware. Now, like we've said before in the CPLD video, knowing this, not having this knowledge is not critical as far as being able to write VHDL code, but it certainly does inform your design and make it better or easier for you to create great designs. So let's start talking about FPGAs. Now, you may or may not realize this, but FPGA stands for Field Programmable Gate Arrays. And basically, these have been around for quite a while. And like I said, they're growing in size and complexity, and they seem to be the direction where programmable logic is moving. CPLDs don't seem to be progressing as quickly as far as new chips coming out. They're really more of a small scale niche market now, and the FPGAs seem to be moving in with some pretty high powered stuff. So from the FPGA point of view, we're going to start by looking at some of the advantages of using an FPGA. And as I mentioned before, they generally have much higher gate densities. So there's a lot more design that you can fit in one chip in an FPGA than typically in a CPLD. Now, these chips, different manufacturers make different versions of CPLDs and FPGAs, so you're going to have some overlap at the margins. You'll find some CPLDs that have pretty good densities and some FPGAs that kind of come close to those low densities. But in general, FPGAs are going to have much higher, greater densities than CPLDs would have, partly based on how they're constructed inside. So generally, they're going to have larger pin counts. You can have pin counts, around 199 pins, all the way up to 600 and something pins for some of the newer FPGAs out there. So there's a lot of opportunity for input-output, high-speed parallel transfers of data, and et cetera, inside an FPGA. They generally tend to be more expensive. In a recent pricing and stuff that I've seen, we're looking at something for some research that I'm doing, and basically we found CPLDs in the price range of about, I'd say $10 to $6 to $10 for a component for a CPLD, and an FPGA at the low pin count area somewhere around $25 to $28. So there's a definite distinct difference in FPGAs versus CPLDs cost-wise, but like we said before, the price varies from model to model and manufacturer to manufacturer, and that probably is going to continue on and on. The thing about FPGAs is they do tend to favor register-based logic. So what that means is register-based logic that is sequential in nature, that has storage elements, lots of flip-flops. So FPGAs tend to have a significantly greater number of flip-flops than a CPLD would, whereas we said before, CPLDs tend to be more advantageous on the combinational logic side, with a lot of combinational logic resources available in them. Now, in the old days, the FPGAs primarily were SRAM devices, which meant that internally the configuration for an FPGA was done by programming ones and zeros into SRAM elements to control the hardware connections internally. What that meant was that when the power went away, the design went away. So you had to constantly load the design in, and that's still the case today with most FPGAs. When you flip on an FPGA in a design, there's typically a serial ROM or flash located close by that initializes, basically sends the stream of configuration bits from the device into the FPGA to program it and get it going, get it up and running. This does take sometimes a few seconds or fractions of seconds, but it still takes time. So it's not an instant on kind of thing. So you'll sometimes see CPLDs used because they do come on fairly quickly, significantly quicker, because the storage is non-volatile. And so when the power is applied, the design is already there. And so they'll come up to speed pretty quick. And FPGA may take a fraction of a second to get up, or maybe a second to get up, depending on how big it is and how much the configuration data has to be loaded. And so that's a factor sometimes. Now, the newer, well, there's two families of FPGAs. There's the flash-based FPGAs and there's the SRAM-based. Now, SRAM is the bigger market. That's a bigger number of chips out there, but the flash-based does have some advantages, and they're getting better. Flash-based simply means that you program the FPGA and the design stays. You don't have to load it fresh. But they're harder to find. There's not as many flash-based devices out there. But they also have some downfalls. Because they're made of flash, their densities are not as good typically. And so there are some performance hits there. So it's kind of a cross between a more dense CPLD with the non-volatile storage if you go with those types of devices. So what you choose really depends upon what your application is, what your price point is, et cetera, and your density of the design. So that's kind of, in a nutshell, the big picture. CPLD is great for combinational logic, smaller designs, smaller pin count things, cheaper. And then the FPGAs tend to be a little more pricey, but they also have a higher density than the CPLD devices, and can hold more complex designs. They're very register intensive, so they can do a lot of state machines and sequential type elements in them without much trouble at all. So let's take a look at how well, first off, before we dive too deep into the structure of each element inside an FPGA, we need to talk a little bit about how combinational logic is done in an FPGA. Now, combinational logic in a CPLD is done with a programmable logic array. That's the and or arrays that we saw in our last video. In an FPGA, it's a completely different structure. It uses what's called an LUT. Now, LUT stands for lookup table. And so by using a lookup table inside our system, it has some limitations, but it also has some advantages, and it's very easy to see how things are done. So let's take a look at what a lookup table is all about. So in combinational logic, we tend to have a series of inputs that come in, and then we have an output associated with those inputs. And the lookup table element is often drawn this way, where you have 3 inputs or 4 inputs or 5 inputs, depending on what your device is, and then a single output. So look at this as basically combinational logic with 3 inputs, and you can have it programmed for any possible output. Now, the LUTs, basically at their fundamental level, are just a multiplexer. That's all they are, where the variables are put in as the select lines for the multiplexer, and the output is programmed by applying constant values to the input of the multiplexer. And the best way to demonstrate this is to kind of do a real quick example of how a combinational logic expression can be implemented inside of an LUT. Okay, so we'll start at the beginning. This is our equation, and we use the same equation in our example for CPLDs. So this is the FPGA equivalent of it. So every Boolean expression can actually be written or drawn or represented by a truth table. And so what I've done here is I've created a truth table that has all the inputs A, B, and C, and then the output X. We went through and looked at every single combination of input here, and we analyzed what the output would be for this particular equation. So then we come up with these characteristic outputs for these inputs. Just a truth table, just a standard truth table. Now, this is really neat because if we use the inputs as a select line for a multiplexer, then if I say, for instance, 7111, that would refer to the seventh element in here, this one up here. And so I can put the value for that, the 0 here, in the input of the mux. That's pretty cool, right? Then if I want to pick out another one, there's 4. So if I take 4, I apply this as the select line for here. That's going to go to input number 4 of my mux. And it's going to take this value here and pass it out as x, just like before. So in effect, an LUT takes the truth table and takes the output of the truth table for that particular variable and writes it, hard codes it into the inputs of the multiplexer. So when you program an LUT with a combinational logic equation, you're basically just writing these ones and zeros as the inputs to the multiplexer, and they're stored internally inside the LUT itself. So instead of drawing a mux, we tend to draw an LUT as a box with the ABC inputs here and the output here, okay? So the inputs and then the output are only drawn, the internal storage is just understood. So if I put in my VHDL code a Boolean expression, such as this, that Boolean expression will be converted into ones and zeros to apply to the input of the mux for this LUT, and then all the variables will be applied to the inputs of the LUT, and then they'll go on the output. Pretty cool, right? So the translation of these that we are doing, now this is how we're representing it since we're doing it on paper. We're going to take the values and associate the zeros and ones with their bit position, okay? So this would be bit 0, for instance, okay? So that's bit 0 because that's entry number 0 inside my table, right? And so this would be bit 3, okay? So that would be bit 3 because that is, oops, I drew the wrong one. Let's do that again. So, no, I was on the right one. I need to pay attention. So that is 3 right there. And that represents bit 3 in my system, okay? So that's bit 3 on my vector, or my value. So now this is the value that gets programmed over here. And then what we've done is we said, all right, bit 0 goes into the 0 position. Bit 1 goes to 1, and so on until we get to there's like bit 5 would go to bit 5 input, and then bit 7, of course, would go to bit 7 input. And that's how we would write it in here. Now, we can represent this value as a hex value by converting the binary value here into its hex equivalent. So it's just the hex value. And then applying that value to the LUT as a value you would program into the LUT. So when you do a VHDL expression and you create a Boolean expression and you're assigning a value of x to this equation, it's basically going through and analyzing and creating this constant value here and programming it into the LUT of choice to give it that functionality. So it's really an easy thing to do if you just look at this as a multiplexer. So any logic in 3 inputs can be done in an LUT, in a single LUT like this. LUTs are not all created equal. In fact, the the Arctic 7 Fpga that's used in the basis board that we've used in some of our demos is actually got 6 input LUTs as part of its structure. So all the LUTs in it are 6 input, and that means they can handle 6 distinct variables as part of the input structure for the LUTs. And so any logic in 6 variables can be done there. If you have more than that variables, like in this case, if you have more than 3 for this particular LUT, then you would have to combine it with another LUT in order to expand that out, which will definitely impact the prop delay as far as your signal delay and affect the frequency that you could use in your device. But that's not something you tend to worry too much about, because when you're writing your VHDL code, you're trying to write code that is generic and applicable to lots of different designs, not just this particular chip. That way you can transfer it to different systems, and then you pick the chip that best fits or best utilizes the resources in your system. Okay, so don't let the chip come before the design comes before the chip. Now, there are going to be times when you want to optimize your design, when you want to get the most bang for your buck. You may have to optimize it by reducing the space it takes up, and that can require some tweaking here and there. But typically, you don't want to do that in a generic design. You just want to create the generic design, do a great job of coding it, and then you should be able to fit it in most devices out there. And you can tweak it if you need to, if you're trying to get into like a low-cost part. So let's say that your design is looking at this part and you're saying, man, this is great because the cost is low, the availability is high. Can we fit it in here? And there are some tricks you can do to get it in that device if the design isn't too big, obviously. So there are ways to code and optimize for different types of chips, but you don't start off doing it that way. Okay. All right, so let's take a look at the structure inside the FPGA. Now, we know LUTs are used for combinational logic, so how does that fit into the overall structure? Well, FPGAs tend to have these things called logic blocks, and the logic blocks are just like the macro cells in the CPLDs. The logic blocks have a number of units in them to help them provide the functionality you're looking for in your design. In this particular example, or in this particular logic block that we're showing, we have a 4-input LUT feeding into a D flip-flop. There's a mux that allows us to choose what the output is represented by, whether it's combinational logic or whether it's sequential logic uses the flip-flop, and et cetera, et cetera. So same as before in the CPLD, we just have these blocks. Now, this is a simple representation. If you go and look at other manufacturers' logic blocks, they're going to vary depending on who the manufacturer is, and the resources they put in there is going to change. And it really depends on what they're trying to do with their chip, what market they're trying to attack. You'll find some devices that have 6-input LUTs or 4-input LUTs or 5-input LUTs. You'll have some that have 3 flip-flops per macro for logic block, or 4 flip-flops. The arrangement really depends on the manufacturer and how they want to piece this thing together. But we're going to do this because this is a simple way to see how the basic elements of a block, LUT, flip-flop, and a number of multiplexers to reroute the signals. If you're really curious about seeing the structure, whatever part you're using, you can go to the data sheets and you can actually see a map of the logic blocks that they're using in that design, how many LUTs they have, how many inputs per each LUT, etc. So it's kind of fun to look into it just to see how that works under the hood. Like before in our CPLD video, let's do an example. And let's do the same examples, actually. We might as well, to show a comparison between the two and see how they kind of are quite similar. So you'll notice here we have the same equation that we had before. This is the same equation we saw earlier in this discussion, and we already went through the process of translating that into a truth table, figuring out what the value needs to be that gets programmed into the LUT. So we saw that with 6, 7. I'm just going to copy that over there. You can do this for any truth table in the variables you want. And so for us, what we would end up doing is we would be coming over here and we would basically write the hex value 67 inside the LUT. And the idea is this programs the LUT for the logic that we're looking for. And the logic we're looking for is going to be, well, we already have the A, B, and C inputs attached there. So this is going to feed through, it's going to bypass and head out the X here. It's going to bypass flip-flop because it's a combinational logic, so we won't be using this flip-flop in this particular logic block. And so that means we'll need to set this value here to 3 hex because we're going to be choosing the third input of the multiplexer that's inside the design to pass the value on to the output. So simply by writing 6-7 here and 03 here, we've programmed this logic block to represent the equation that we've shown right there. Okay, pretty simple, right? So LUTs are kind of cool. So when you see specs for LUTs and FPGA, or sorry, see specs for FPGAs, they'll oftentimes give you a table showing the number of LUTs and the number of flip-flops that are in this particular device, and that gives you an idea of how big a design you can put in that device. And that's very helpful for deciding which device is going to be best for your particular application. All right, so let's take a look at the second and last example. This is the last example where we're going to create, like we did last time, a toggle flip-flop. So the idea is to implement a toggle flip-flop, which means we're going to be using the flip-flop in this. It's going to be a synchronous design. And let's go ahead and draw the pathway. So obviously we're going to be applying a value here to the D input. And again, this reset and clock are attached to universal clock and reset, just like in any good synchronous design. We'll have a common clock and a common reset. The output then will come out here. We'll just use the, well, actually we could, well, there's a bunch of ways we could approach this. We'll use the non-inverted output, although we could use the inverted output, but it doesn't matter. So in this particular case, we're going to do that, and then we're going to need a feedback path to come back into this input 3 here. Okay, and that feedback path is going to need to cause an inversion on the signal. So in order to create a toggle flip-flop, whatever is sitting here on the output, right? So whatever's on the output right here, that needs to feed back into the logic, and then it gets inverted here. So this is basically just an inverter that we're going to create in this LUT. Yes, I know we're wasting a lot of inputs on the LUT, but that's just the way it goes, right? We need an inverter, and this is where we can do it. Now, in truth, a lot of the logic blocks that you'll find in FPGAs actually do have elements in them that will provide the inversion without going through an LUT. You'll see things like exclusive OR gates with programmable bits. Those are actually programmable inversion elements. But we're not going to dive into that too deep. We're going to just go through the LUT and see how to do that. Now remember, before, all we have to do is figure out what value to put here and what value to put here. Those are the two values. We want the LUT value and we want the multiplexing value. So to do that, we need, pardon me, we need to draw a truth table. So in order to do the truth table, let's go ahead and do this by hand. And we're gonna just, it's only 8 entries, so let's kind of zoom in on it up here. We'll do this by hand. We'll have these are in this case, we have I3, I2, I1, and I0. We're not using A, B, and C, so we really don't need to worry too much about those. Those are I0 through I2, but we're using I3 as our input. So what we're going to do is we're going to draw this little truth table with I3, I2, I1, and I0. Okay, so this is actually 4 inputs, so we'll have 16 elements in here. And then this will be our output. And if we draw the truth table, okay, so I'm going to have to, this is going to get a little longer, 0, 1, and 0, 1. So we're going to do 16 entries in here. I'm going to use a slightly thinner, different line so I can help distinguish these so we can see how this is going to pan out in our particular design, okay? Now with it being oops, my lines are just not quite perfect, but they're pretty close. So in order for this to work for us, we're gonna have to think in terms of, hey, we're not using these inputs. What do we make the other inputs? I'm gonna default to 0 if it really doesn't matter. Well, sorry, it does matter. For all of them, it's gonna matter. All right, so let's take a look. Let's draw, oops, wrong line color. Let's draw this, wrong weight. There we go. And then this will be 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 1, 1. And then we're going to go 0, 4, 1, 2, 3, 4, 2, 3, 4, and 1, 2, 3, 4. The old trick of drawing a truth table by hand is with each successive column, you create the number of zeros and ones based on the power. So this one would be the one here. This would be every 1, because that's the power of 1. This is every 2, because it's a power of 2. This is every 4, that's the power of 4. And then you'll do 8. So this is 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 6, 7, 8. Okay, so there it is. That's all of our inputs. We really don't care about I2, I1, and I0 because they don't impact the output at all. All we care about is the value that we put in I3, because remember, I3 is the feedback path here that goes into the LUT. And so all we're doing is inverting it. We want to create an inverter. And so to do that, we just look at that and we write the opposite. So this is, there's 0 to 1 there, and then this is going 1 to 0, like that. And so if we look at that, we can see clearly that if it was a 0, it becomes a 1. If it was a 0, it becomes a 1. If it's a 1, it becomes a 0. You know, a 1, it becomes a 0, and so on for all 16. Now we've got the number we need to program this with. So this is going to be right here. This is going to be bit 0, and this is going to be bit 15. It's a 16-bit value, which means that our value binary that we would program into the LUT is going to be 8 zeros followed by 8 ones. We know that's pretty easy as a hex number. That's a hex number 00 fox fox. And so down in here, the LUT would have 0, 00 fox fox as part of its programming. Okay, and there you go. We've programmed the LUT. This is going in through 1, so that's 0x1. That is the pathway we're creating with the mux. So to create a toggle flip-flop with this logic block, we would program the LUT with the value 00 fox fox, and then we would program the mux with a value of 1 to select that path from the D flip-flop, and we've programmed it. And we're done. And this actually acts as the hardware that we have asked it to. The LUT is being used as an inverter. So it really is a matter of writing and drawing the truth table, reading the values here, and then translating those values into a binary number, and then writing that as a hex number, and then putting it in our little table here. So we do this, the software, the implementation software that we use for FPGA design and CPLD design, the synthesis software, it handles this for us. It does. It creates it, figures out all the numbers for us. We don't have to worry about it. But I think it's very instructive and important to understand what's really going on in the hardware. It is not that complicated. The algorithm for doing this is incredibly complicated. But the process of writing a value into an LUT or writing a value into a mux control, a select control, is just, it's just putting values in basic digital logic. Hopefully this has been instructive and helped you understand a little bit more about how FPGAs work on the inside. Like we said before, you can use this knowledge to your advantage. So if you're trying to create a very optimized design inside an FPGA and you're starting to run out of room, you can do fun little tricks. Like, for instance, let's say that you're creating a state machine with a number of states. In a register intensive machine, you could do what's called one-hot encoding, which would give each state a bit and since this is a heavily register intensive device, there's tons of flip-flops, you can reduce the number of LUTs you use by doing it this way significantly. So you can have a significant impact on LUT usage. Like I've said 100 times before though, you don't design based around particular hardware. You resort to these kind of things if you're really trying as an engineer to design and fit your design into a particular device, and you're finding yourself running out of room. You can play games with this and at least scrape off some excess size and make it fit as well. And it might even affect your performance as well. So smaller LUT paths can result in higher frequency because you're not going through as much combinational logic. So there's lots of little tricks you can play. So hopefully this has been helpful, and we've learned a little bit about hardware. Thanks for watching, and see you in the next video.